Okay, so I'm actually going to be giving my talk in the reverse order that's listed on the title. I'm going to first talk a bit about the data, haystack of high-dimensional data. Then I'm going to talk a bit about how we extract the needles or find the interesting signals in our data sets before moving on to talk a bit about the particular work that I do in developing statistically robust methods for doing said extractions. Okay, so earlier this year there was a nice issue in Science devoted to discussing the very interesting challenges and problems and excitement of all the vast digital data that we're able to generate these days. And just want to highlight a particular perspective piece written by Rich Baranook in the Electrical Engineering Department at Rice entitled More is Less, Signal Processing and the Data Deluge. And Rich's focus there is mainly on sensor data and the plethora of sensor data that's being generated these days. And he gives several examples. But one of the examples that I found particularly interesting I want to share with you is this very fancy camera that DARPA has put up on this satellite. Just to tell you about this camera, it's got 1.8 gigapixels, it's got a field of view of 160 square kilometers, it has a very nice ground resolution of 30 centimeters, and when it's doing video capture, it's at 15 frames a second, you're staring at about 770 gigabits per second. So Rich goes on to talk a bit about the interesting challenges in processing and analyzing this data. It's kind of a reversal of fortunes in some sense. Like in the past, we just weren't able to generate a lot of data. Now we almost have too much data. Okay, so the focus of my talk today really is like, how do you make sense of all this data, right? And a key observation is to realize that information is not really uniformly distributed across all the measurements. And there's just pretty basic idea I think everyone's familiar with that really helps us out in dealing with these types of data sets, and that's, you've probably heard it called Pareto's principle or 80-20 law. And that's just basically the idea is that 80% of a particular effect you're interested in is usually caused by only a small fraction, relatively small fraction of the possible causes. Okay? So the story goes that Alfredo Pareto observed that 80% of his peas were coming from 20% of his pods. He had the little bit more famous observation that 80% of the land in Italy was held by about only 20% of the population. And there's lots of other examples I think most folks are pretty familiar with. But when you move to the context of data analysis, for a statistician, we like to use the language of sparsity. And kind of rephrasing this principle, the idea is that the majority of the systematic variations really probably only due to a minority of possible causes. Okay, so how well founded is this assumption? So let's just look at two examples. And my first example involves my son right here, and a little picture of him. And what I'm doing here is I'm taking this image, my signal y, and I'm going to re-express it in terms of another building block signals, basis functions. In this particular case, wavelets. Okay, and I'm looking at the contributions of each wavelet that go into this signal and representing this signal. And what I've plotted on this view graph here at the bottom is I've taken the absolute magnitude of all the wavelet coefficients and just sorted them. And this is on a log scale, and the first thing that should probably jump out to you is that a vast majority of the energy in the signal, once you've looked at it in the right perspective, in the wavelet domain, resides in only a small fraction of the wavelet coefficients themselves. Okay, so there's a neat little party trick. You identify the most significant factors, and you invert the transformation, and voila, very low loss reconstruction of the original image. Okay, and this is all very well known stuff. Everyone in this room is probably familiar with JPEG. It's not doing a wavelet transformation there, it's doing a discrete cosine transformation in addition to a bunch of other stuff. But certainly in the case of digital imagery, it's pretty well known that there exists some representation, some basis in which you can find a sparse representation that can be exploited. So moving on to my second example with genomic data, here's the following setup. Imagine you have two groups of people, and there's a particular study I'm going to talk about right here. And the one group has a susceptibility to infectious disease, leprosy, and the other group doesn't. And one of the first thoughts you think about is maybe there's some type of genetic differences between these two groups that can explain this variation between them. So these days it's possible to very comprehensively query the genotypic status of individuals. You can even send samples off to 23andMe and they'll do something like this. But essentially, when you have a study like this, genome-wide association study on leprosy, you're able to take maybe about 1,000 cases, 1,000 controls, and take about 500,000 measurements or so on genotype state. And again, it's great that you're able to take such a comprehensive set of measurements, but quite frankly, it'd be very surprising if all 500,000 of those SNPs actually had anything to do with predicting the differences between these two groups. So there's biological or physical reasons why you'd suspect or be interested in finding a sparse model. Okay, so I have a couple of these summary slides throughout my talk, and I was inspired by some of the reading I do with my son at night to use the vehicle of words of the day to kind of summarize the key points. And so the first letter of the day is S, and S is for sparsity. Okay, so we're talking about this high-dimensional haystack, and you have all these possible measurements, but really some of them are more important than others. Okay, so this notion of sparsity is going to be really key in helping us to analyze and figure out where is the interesting behavior in our data. Okay, so that's great. You're looking for a sparse model, but how do we go about actually computing and extracting this sparse model? And I want to tell you a little bit about kind of what's been widely and absurdly, almost absurdly a successful procedure for extracting sparse models that are actually very good at making predictions. And so we're going to take a little excursion to review a bit about penalized regression. Just to orient you on the framework here, it's an optimization problem. I'm trying to fit a mathematical model to some data, right? So here's my my output that I'm trying to model, and I'm just going to look at some linear models to try and match that. And this L function here is just a lack of fit. I want my model to agree with my data in some sense or another. And I also am concerned about the complexity of models, and in particular sparsity. I don't want to include too many predictor variables, okay, for example. So J is capturing the sparsity of my mathematical model, the complexity of my mathematical model. And I have this tuning parameter lambda, and it's a two-criterion problem here. I just want to be able to trade off the complexity of the model with how well it fits with the data. Okay? And we'll just go through a very classic example of the least squares regression, just to go through some expressions that I think really can highlight why a particular type of penalty parameter on the complexity has been very successful at recovering sparse models. Okay, so I drew a little cartoon for my mathematical model here, and the main thing that I want to highlight here is that this matrix X is short and fat. Okay, it has way more columns or predictors than it has rows. Okay, so this is, as everyone recognizes, is way more unknowns than equations. So it's got infinitely many solutions, which is not particularly useful if you're trying to understand your data. And this is kind of the first place where you can see where adding a complexity component to your fitting procedure can help you out. I think a lot of folks that do these types of things are familiar with using Ridge or Tikhonov penalization. And all we're doing is taking as our penalty function on the complexity to be the squared 2 norm. Okay. And this is helpful in the sense that we can actually extract then a unique solution, but it doesn't really help us in terms of sparsity. Okay, so it's going to turn out that you're able to compute a regression coefficient theta, but it's still going to be pretty dense, not many zeros. Okay, so it doesn't help us in terms of interpretability. If you think about it, what we'd really like to have is a penalty on all the total number of non-zero terms in my regression vector here. But that's if you plug that complexity penalty there into this problem, that's a combinatorially bad situation, right? So that's not really computationally feasible. Which leads us to a computationally feasible solution, which is to let J be the L1 norm. So I just take all the elements of my vector, absolute value, and sum them up. And it turns out this is a fantastic surrogate measure for that combinatorial measure of complexity that I mentioned before, the total number of non-zeros in your vector. Okay? And I just want to walk a little bit through some of the details of the characteristics of the optimal solutions to give you a sense of how it works. Okay, so listed here are the particular loss functions I'm trying to minimize, and these are the global optimality conditions for the minima that they have to satisfy. And the first thing I want you to notice is that there's a lot of similarity between the three things. And then the second is there's a little bit of differences. So let's first talk about the similarities and the common components. So what's this RJ? RJ is the jth partial residual, and essentially it's just capturing how much variation there is in left over that's unexplained if you use all your variables in your model except for a particular one, the jth one. And then, I'm taking this inner product between the jth residual and partial residual and the jth predictor, and that's just essentially correlation. Okay. So what you can see here is that in the ridge case, there's just a rescaling of the optimality conditions. But there's not going to be necessarily any changes in terms of the density of the solutions that you're going to get back. Something interesting is actually happening, though, with the L1 penalized solution. Okay. So this S function here is a soft thresholding function. And what it does is, as an operator, is it shrinks your solutions towards 0. And it does it in a very nice way, the following way. If you're within your threshold bounds of lambda, your input gets shrunk all the way down to 0. If you're outside that band, you get shrunk by amount lambda towards 0. Okay, so just recall the optimization problem and the global optimality condition I have here. I'm taking these correlations and then shrinking them towards 0. So essentially what this is doing is that if your predictor variable is not particularly well correlated with your signal that you're interested in, the output measurement that you have, you threshold that down to 0. Okay, so low correlations end up being thrown out. Okay, and so it does this in a very systematic and principled manner, and it's easy to solve, relatively speaking, a lot easier to solve than a combinatorial problem. But one problem about this, or maybe it's a feature, is that the solutions are biased towards 0. Okay, and so that's, or before I move on to the next one. So the second letter of the day is E, and E is for L1 penalized regression. Okay, so if you want to find sparse solutions, then the way to approach that works very well is to do L1 penalized regression. All right, so which leads me to discussing some of the stuff that I do with robust estimation procedures. I'm going to look at particularly one nonlinear-ish model for the logistic regression. This shows up whenever you have binary data, like with our genome data example we discussed earlier. But this also shows up, it's a classic method in machine learning for classification. It also shows up when you're trying to learn graph structure. But here I have a much simpler case here. So just to review, I just have a single predictor variable. And I'm trying to estimate the conditional probability that I'm a 1 or a 0. And this is simulated, so this black line is actually the truth. And I generate these data points from the black line. And I just did the standard maximum likelihood estimation to generate this orange curve. Everything looks great. Okay. So what happens if I toss in a couple of outliers? Okay. And when I do that, you'll notice that the MLE curve flattens out. Okay. And so this is bad in the following sense, because this slope at this transition point right here, and this inflection point, is actually directly proportional to the norm of my regression vector. Okay, so it's flatter, that means the norm of my regression vector is going to 0. If the norm is going to 0, the regression vector is going to 0. Okay, so I'm missing effects or explanations. I'm losing explanatory power. Okay, and so this is, it turns out when you have outliers and you're doing logistic regression, there's your solutions that are getting biased towards 0, and they can only be biased towards 0. And this is called implosion breakdown. Okay. So I just have another little simulated example here. I have one true predictor variable that's generating my data, and I've thrown in 9,999 noise covariates, right? And you expect, and you'd like for your L1 penalized logistic regression model to extract that one relevant predictor, right? And in the clear case, you see that. So in the bottom rows, you see what are called regularization paths. And so I'm just tracking the coefficient values for all 10,000 variables as my penalty parameter lambda decreases. Okay? And you'll see in the uncontaminated case, you get the nice separation that you'd like to see. But as you add contamination, you're losing that signal to noise ratio because of that soft thrust, that implosion breakdown. Okay, and of course everyone remembers what's really going on here is that when you're doing this variable selection with this L1 shrinkage or L1 regularization, you're biasing your solutions. And so these outliers only bias your solutions more. And so when you do this model selection step through this L1 penalty, it's just too much bias towards 0 to overcome. You lose your signal. Okay, so really briefly, how do you deal with this? Well, you just change your optimization problem. Okay, you change your loss function that's not robust outliers to one that is, and the particular choice that functions that I work with are called beta divergences, and you don't need to necessarily know all of this. All I want to point out is that it's just a discrepancy measure between probability distributions. So here's what you're trying to estimate, and here's the models, and you're trying to find a good model that minimizes this discrepancy. Okay. And again, all I wanted to point out here is that you can also write down the optimality conditions in this situation. And the only differences between these two are that you have this extra term here, and this downweights the influence of some observations. Okay, so really quickly, if you swap out your loss function like so, you can see that you add these contaminants, but now you have regularization paths that aren't influenced. Okay, so obviously I've skipped over a lot of the details. The hard part about this is working out the computational algorithms. Just one point about that is that when you swap out the loss functions, you're now working with a non-convex problem. So, but what your goal is then is to turn to solve a series of convex approximations, and then you're kind of back on common ground, but you've created more work for yourself. Okay, so I'll end here with just the last letter of the day, which is B, and that's for bias. And so L1 penalization bias plus implosion breakdown bias can lead to misdetections. And so if you want to deal with this, you need to change your loss function. So with that, I just want to say thank you for your attention. Happy to take questions.